precision versus accuracy, mean point of impact variability, and some recent testing we've been doing at RAD on this benchtop discussion. Hi guys, it's Peyton with Reloading All Day, here to bring you our first benchtop discussion. This series is coming out of a need for us to more thoroughly explain some of the finer points of precision rifles, reloading, internal ballistics, and any other subjects that we may feel the need to expand upon more than, say, Instagram comments or Facebook comments will allow us to. By bringing our content to a more visual manner, we're hoping that we can get the point across and hopefully teach some people more things than we're able to through our social media pages. So without further ado, we're going to jump right into this benchtop discussion. So as of recently, Blake has been doing some 223 specific testing. We have noticed some discrepancies on the 223 specifically when it comes to velocity consistency that we don't see with any other cartridges that we reload for, and we wanted to get to the bottom of what was happening there and try to focus specifically on 223. You've seen some of the velocity testing that he's been doing, some accuracy testing, large sample sizes, 100 shot samples, 100 shot groups. You've probably seen them out of the AR. This research started on gas guns specifically, and trying to kind of tailor this research focus to them. It has since evolved to encompass our bolt gun testing. We built a bolt action 223 rifle specifically for this testing to try to narrow the variables that we have when looking at velocity consistency of 223. Since we got the bolt action put together and we've been testing with it, I have asked Blake to do some 223 precision testing as well, specifically from this bolt gun. And that's to validate some of my research that I've been doing into the statistic modeling of rifle dispersion, especially across large samples. So this benchtop discussion pertains to some Instagram comments that we got on one of our posts in August. One of our followers had a conversation with us about how our method of overlaying groups is more indicative of shooter skills than it is the inherent accuracy or precision potential of a load and rifle. And we disagreed with that. And we had a conversation with this follower, and we thought that it would be best to expand on that in a YouTube video and why we don't believe that overlaying the groups specifically is less indicative of rifle performance. So when we talk about precision versus accuracy, of course, we have to review what precision versus accuracy is. It's been done by just about everybody who writes in the precision rifle space, but we'll do it again. We've all seen the 4-target graphic of precision versus accuracy, where you've got one target has high precision and low accuracy, another target has high accuracy, low precision, third target has high accuracy and high precision, and then your fourth target, of course, has low accuracy and low precision. So we've seen all that graph. We've all seen that graphic. And to apply that to us as shooters, we, of course, are talking about precision being how tightly clustered our shot group is, accuracy being how centered that shot group is on where we were intending to hit on our point of aim. This gets talked a lot about at longer ranges, specifically because you need both accuracy and precision to typically hit your target. Precision, you need to have a precise rifle. You need to have a rifle that shoots good groups. You need to have a rifle and load that cooperates. And you also have to have accuracy, which is, how you input things into your ballistics calculator and the firing solution you get for your rifle to make those hits at longer ranges. So, what does this mean for us testing precision? Well, initially, Blake had fired a couple of 100-shot groups because we were mainly looking at velocity. We weren't really concerned about the precision of the rifle. And so when that was the case, just for demonstration purposes, Blake would fire all 100 rounds into one single ragged hole. And the hole was, it was large. When we did those tests with the AR, it was like 1.2, 1.3 MOA extreme spread. And so excellent performance out of a gas gun. But what that does when measuring precision is a lot of that data gets lost in the center of the group. So you fire and you're firing more rounds, and as that group encompasses kind of your aiming point, or if you've dialed off your aiming point like you should when firing large groups so you don't shoot it away, is that a majority of your shots are going through the center of the group. And when you have large samples like that, 20, 30, 50, 100 rounds, some of the bullets later in the string pass right through the center. They don't leave any marks on the paper. They're just flying through open space. So when it comes to precision testing, it's not exactly optimal. And because of this, I asked Blake to kind of switch 5-shot groups. When we went to the bolt action rifle, that was about as many rounds as we could fire at a single aiming point before we kind of lost definition on where each shot specifically landed. With 5 shots, we can track each shot specifically, and we would fire 20 groups of 5 rounds for 100 shots total. And the comment did come up that, because the shooter is getting up, is repositioning, is rebuilding a position between groups, that this was more that our methodology of overlaying all the groups is more indicative of shooter consistency and shooter performance. Now, there's a few main reasons that we think this isn't happening. First of all, the shooter is contributing very little in this case, based on the position of them. The rifle is extremely, extremely heavy. Recoil is very light, 223. And if the shooter had a significant influence on precision, we would expect that to manifest as different levels of precision from day to day and week to week, because if the shooter is inconsistent, then we should see inconsistent levels of precision. And then our final point here, even if the shooter had a significant influence on precision, we wouldn't expect it to manifest as an accuracy error. So I'm going to go back through these a little more in detail. Of course, the shooter is contributing very little in this position. Blake is either firing these groups from the prone or off a bench rest and a bipod and a bag. Very, very solid position, very repeatable position. I really think that the shooter, Blake in this case, is fully capable of being extremely consistent from this prone or modified prone position. And I really think that most shooters should be able to outshoot their rifle from this sort of position. Very stable, very consistent. If your wobble zone is the limiting factor in a prone position of your rifle's precision, you should probably get your heart checked or something, or see a doctor, because I don't think that's normal. And so shooters, while I generally agree that shooters are the weakest link of the rifle system, from the prone, I think there's bigger things at play than shooter influence in the rifle system, specifically from prone, modified prone, and with a very, very heavy rifle. You'll see here, the rifle weighs like 17 pounds. We have a 1.25 straight contour barrel on it, and the Vision Pro chassis. It's heavy for a 223, and it recoils very, very little. So if shooter inconsistency, I could believe that shooter inconsistency would cause issues with a lighter rifle or a heavier recoiling rifle, but in this case, I really think that 223 in a heavy rifle is light enough that we're not really seeing recoil effects to the extent of the muzzle deviating from the point of aim during the recoil impulse, because the rifle's barely moving at all. And so for our third point, if the shooter had a larger influence on the system, we would expect that to manifest itself as inconsistencies from day to day and week to week. But we don't see that to be the case. Here we have an 84 shot group out of this rifle. Mean radius of 0.217 MOA. This is max spread of 0.954 MOA. This one, 100 shot group, 0.846 MOA. This is 99 shots. This is 0.198 mean radius MOA. This one, 95 shots, 0.229 mean radius. This one, 0.890 MOA mean radius. We are seeing this rifle perform very, very consistently day to day, week to week. And it continues to produce precision results with an SD X and Y average of about 0.17 MOA. That is stellar performance. And if the shooter was influencing the system, we would expect more inconsistency in that precision SD. We would expect to see more variability in the system. So we expect that the shooter, in this case, is not influencing the system very much. And to our final point, if the shooter did have a significant influence on precision, we would expect that to manifest as a precision issue and not an accuracy issue. So to illustrate this, say your rifle has some precision, that is the group that the rifle fires unaided, unadjusted by a human. Then say you've got, some human element to it. This makes this a little bit larger. This should be circular around this. This is what your total precision would look like. And then if you were to shoot at longer ranges, then you would add in the environmental effects that go with shooting a rifle. Now, this is for, wind uncertainty, range uncertainty, all the things that play into a long distance shot. Now, because we're shooting these groups at short range, we can take out most of our environmental factors. So that can go away. In reality, it is still there. It's just extremely small if it were to get added onto this human error. It would probably only be minute. At 100 yards, those effects are very, very small. And then, of course, because of the position that we've built for our shooter, most of our human error can go away. And so, on top of the precision of our rifle that we might have a little bit of shooter influence. Maybe just a touch. But at the end of the day, I really do believe that the shooter influence is smaller than the total precision of the rifle when locked down in a vise or in a UR. When you remove all those first order effects of the recoil impulse, I really do believe in this case, because of the heavy rifle, the light recoil, the bagged position, that shooter influence is smaller than the precision potential of the rifle. Even if it wasn't, it would be extremely small. But notice how this is only growing the group size. These two circles are concentric, because shooter influence, assuming a good position and good natural point of aim, shooter influence will only be increasing the size of the group. It will not manifest as an accuracy issue unless the shooter is inconsistent in their positioning on the rifle. You can ask silhouette shooters or some of the more like service rifle. You can ask those guys that shoot from field positions that the group size just grows when you bring shooter influence onto it. It doesn't change position. The group size is still relatively the groups are still relatively round. It's just that you have larger groups. As long as the shooter is being consistent in their positioning behind the rifle, which we fully believe Blake is. He's a very good shooter. So, in addition to these things, you also have the sampling that goes into each group. So, for 20 groups of 5 shots, for 100 total shots, what you see on the paper, there are 75,287,520 combinations. Those shots could have fallen into groups. If you're one of the people that believe the order of the shots matter as they came out of the rifle, there are over 9 billion permutations of one single test target. This means that, while we've got this overlaid group here, pick one shot out of the group. Let me make sure you guys can see that a little better. Pick one shot out of the group. One shot. That shot could have fallen into any group on the piece of paper. That shot could have fallen at any point in time. The position of these shots is determined by a number of relatively randomized factors. We're talking powder charge weight. We're talking the specific primer and the primer energy that has. We're talking pointing vector of the rifle. We're talking about the exit velocity at the muzzle. All of these shots well, if you believe they're predetermined by the conditions that exist, well, it's kind of true. There is a set of characteristics that defines where each of these shots falls. And if you could, measure that precisely enough and model an equation precisely enough, you could predict exactly where each of these shots will fall based on the conditions that exist. So each group is made up of relatively random shots within this large cluster that we tested. And because of that, one group isn't really the data point we're looking for. And the movement between these groups, the movement, we'll get into that in a little bit, isn't anything except dispersion appearing on target. The actual way to do this in a very scientific manner would be to fire one shot at one dot. We're firing groups of shots because it's more efficient test-wise. Single shots at single points turns into extremely large targets. It turns into handling that data analysis. It makes data analysis really clunky. And so, of course, we are trying to be efficient in our testing. And so firing groups shrinks target sizes. It makes data analysis a little bit easier for us and generally just makes life a little bit better. But at the end of the day, one shot is a data point, not any one group or even any number of groups. The shot is the data point for precision testing. And that's why we decide to overlay the groups instead of, take an average of the group size. And so that brings me to my camera dying very rapidly. So this brings us to the main point of this video. This all culminates in the phenomena of mean point of impact variability. And what that is the tendency of measured group centers to be misaligned with one another, just due to the nature of dispersion. You don't even have to take my word for it. You can ask Jeff Seward. Here, it's in his book, page 367, mean point of impact and MPI variability. The mean point of impact sigma equals the sigma of the true dispersion over the square root of n, which is the number of rounds fired for your sample, number of samples tested. So what does that mean for our rifle that fires 0.17 MOA SD? That means that we have a little bit of math here. Where my calculator? What does that mean for us? We have 0.17 divided by the square root of 5. And we get 0.076 MOA. That is the mean point of impact variability that we would expect in the vertical and horizontal directions expressed as a standard deviation. So if you multiply that standard deviation by 4, that would be 0.076 times 4. You could expect up to, for a 95% confidence, up to 0.3 MOA of your group center movement in the vertical or the horizontal direction total. That's across the entire thing, for 5-round groups. So we can see the effects of mean point of impact variability right here on our target, or on one of our test targets. Each measured group, the center of, is indicated by this cross, and each group you can see doesn't have the center fall exactly in the same place. This one's here, this one's right there. And then you can see that the center moves a little bit. And people point this out and say, well, by overlaying the groups, you're taking into account accuracy errors, shooter influence. Well, this isn't necessarily shooter influence. So our .076, if you express that in a number of standard deviations, we can do 2 standard deviations to encompass 68% of the expected data set, or 4 standard deviations for 95%. So if you take .076 times 4, that's 0.304. MOA from left to right and up and down that the center of these groups could fall within in 95% of the time. So this group here is about in roughly the average of where all these centers fall. And so 0.3 MOA edge to edge would end up being kind of a box like this. And if you put the corners in there and then make that a circle, that's about where we expect the centers of all of our 5-shot groups to fall within. That is our error budget, so to speak. And you can see that, this one's pretty far on the right side of that, but it's in there. This one's a little lower than that other one was. This one's off towards the right. This one's off towards the left, but it falls within what we expect. And so we can only assume, because this mean point of impact variability is based on the distribution itself, we can assume, in this case, since there's nothing falling outside of the expected values, that shooter influence is minimal or none. So to prove MPI variability to myself and this equation, I did a little bit of simulation. I did this quick and dirty in Excel. I eventually want to do a cleaner code version of this in Octave. But Excel had to do for now because I wanted it quick and dirty. What this does is it simulates 100 5-shot groups. Now, the important part about simulation and why it's so powerful is I get to define what parameters are being used. So when we go out and actually test, when we live fire, the true center of the true dispersion is unknown. We don't ever know where that is. We can guess, we can fire more shots and get a better idea, but we never know precisely where that point is. That's the same, that is the same for dispersion SD. We don't ever know the true value of the SD. We can estimate, we can calculate, we can do all kinds of things to try to obtain that, but we don't know what the true number is. We can get pretty close, but it takes a lot of shots. So the simulation is powerful because I define where the center of the distribution is. I define the SD of the distribution. I define that right there. And so I can calculate with certainty how far all these shots are, all these groups are from the true center of the distribution, and get the deviations from center. That's something we can't do in live fire. So you see here, we have a mean of 0. The group or the distribution is centered on 0, 0. The SD of 0.17, that's about what we're expecting out of the 223 bolt action right now, 0.17 MOA SD in the X and Y axes. You go through the positions of each shots, and then you calculate the center of the group. And from there, you can get the mean point of impact deviation from the center of the distribution. You can get radial deviations of each shot. You can get the group, extreme spread, and mean radius. Now, what I want to draw your attention to here is that this is a 0.17 MOA SD rifle. Average extreme spread 5-shot group, 0.55 MOA. That's pretty good. It's about what we're seeing out of the 223 bolt gun. Minimum extreme spread, 0.259 MOA. Pretty small. Max ES, 1.11 MOA. Not quite as small. This is the variability that you can expect out of 5-shot groups. This is 100 simulated 5-shot groups. And this is about what you would expect to see. You could have this. You could see this on a piece of paper when you live fire. That's just the nature of dispersion and sampling the distribution. So when you get down to it, the important numbers are here. The deviation, SD, X, and Y. In this case, that is 0.079 and 0.076 MOA. That is around what the equation gives us of 0.076 MOA for the MPI variability SD. You're not going to get perfect numbers out of simulation because it's not idealized like the equation is. You can get very close, and as you approach infinite groups and infinite samples, you should get closer and closer to the data that you expect to see from the equation. In another instance, this is a rifle that, maybe more people would have access to. I don't think that, maybe people will have a rifle that averages half MOA 5 shots, like across its entire lifetime. But when you get into high sample sizes, it tends to be that most people do not. So here's another example of an SD of 0.23 MOA SD. Again, the distribution is centered on 0, 0. This is another 100 groups of 5 shots apiece. The equation that we expect is 0.23 divided by square root of 5. That would be 0.103 MOA for MPI variability. Down here, deviation X, deviation Y, 0.113, 0.094. That about averages what we would expect to see, or what the equation gives us. So I think that the equation is good, and you should take into account the amount of rounds you fire into a group and what your variability of mean point of impact would be. This gets worse as you fire less shots. 3-round groups. Here, I just our MPI SD, our MPI variability, we would expect to see 0.076 from 5-round groups for the 223. For 3-round groups, 0.17 divided by square root of 3. We would expect to see 0.098. That's quite a bit more. As you go up in groups, as you fire more rounds, that variability goes down because you're sampling a larger data set, and it works in your favor. For 10 round groups, 0.17 divided by square root 10, that drops to 0.05, so about a third. It goes down about a third, going from 5-shot groups to 10-shot groups. As you increase the sample size, the uncertainty of where the center of your group drops. And that is the basis of why when Hornady's podcast came out a couple of years ago about your group sizes being too small, I remember specifically a couple of PRS shooters started zeroing their rifles with 20-shot groups or larger sample sizes than the standard 5 that was standard back then. And those guys said that they experienced less zero shift from day to day from their rifles. And what I expect is that they cut down their mean point of impact variability to an extent that the variability of it wasn't seen in day-to-day groups. If you fire a 10-shot group or a 20-shot group to get a 0, you are much more certain about where the center of that group is. You're much more certain than if you fired a 5-shot group, zeroed based on it, and then maybe came back a day or two later and fired another 5-shot group. Well, it could have deviated, depending on the precision of your rifle, 0.1, 0.2 MOA. It's there, and it's a real effect. And because our testing falls within the expected values of mean point of impact variability, we don't think the shooter is having a huge impact on this precision testing. At the end of the day, if you couldn't human fire precision testing, I don't know of anybody that would do it. A lot of companies do precision testing with human shooters. And we're going to do a little bit of testing in the future comparing a human shooter with a ransom rest with this 223 rifle. I don't expect to see any difference in precision between the two of those, but we'll get you that video when we conclude with that testing. So, to review, we don't think that our methods are in any way disingenuous about the precision of the rifle system because of the skill of the shooter, the weight and the recoil characteristics of the rifle, the stability and repeatability of the positions, and the data that presents itself to us through mean point of impact variability. And this is a great example of low sample size testing kind of muddying the waters about what's truly happening in a rifle system. You have here a precision or a distribution sampling error, sampling size issue that gets classified as an accuracy issue because it looks like one in the small sample. But as you push those samples higher and higher, the issues go away. Your uncertainty becomes less. Mean point of impact variability goes down. Group size variability goes down. Things are rectified by testing in high samples. Now, does that mean that you need to do it all the time? No. This hobby's expensive. Ammo and components are expensive. And we don't want you to have to waste your money or your time. Your time is probably more valuable. We don't want you to waste any of that for yourself. We're doing the high sample size testing to show you what is occurring and what low sample size may be hiding from you, or show you that you think, or show you something that you think has an effect. We're doing this testing. We always are doing high sample size testing to show you, because we have the time and inclination to do it. And the next best thing, if you can't do high sample size testing for yourself, is to learn what low sample size is showing you, to learn what is muddying the waters, to learn what fallacies to avoid. That's the next best thing you can do. Because then you have an awareness of what you might be looking at when it comes to low sample size. You now have MPI variability. You now have, through this equation, another tool in your toolbox to analyze your groups on paper and to show yourself that, oh no, my zero isn't walking. This is just the dispersion of the rifle. And if you need to go and prove any of this to yourself, all of our testing can be duplicated, can be replicated by you. You can do all of this. You can do anything that we do, whether that's simulation or live fire. You can do it yourself and prove it to yourself that we're telling you the truth. Because at the end of the day, we want to get the best information that we can to you as shooters, because we want to save people time and money at the reloading bench, and we want people to be more confident in their rifle systems. We spend a lot of money on these rifles, on this ammo, and it's disheartening to not be confident in your rifle, in your ammo. And this is why we harp on using things like mean radius or standard deviation of dispersion to measure rifle precision as a holistic kind of look, overlaying groups, using larger samples. That's why we do this, because while those numbers may not look as impressive as a couple of 5-shot groups that turn out pretty good, it gives you a better baseline of what the rifle is capable of on a normal day. This is the performance that you should expect every day out of this rifle, because you've gotten a better sample of it. And a good performing rifle is still going to perform good. You just have to adjust your mindset to the numbers that you get out of different measurements of precision. But your rifle doesn't shoot nearly as good as you think it does. Probably. And most people don't understand that. And so, I have nothing else for you today. If you like this format, this is very new, very different for us at Reloading All Day. If you like this format of me sitting in my basement, just giving you this, not really stream of consciousness. I've got some notes over here, but this is very unscripted. This is very mildly edited, chopped up a little bit, but not a ton. So this is stream of consciousness. If you guys like this format, please get in the comments, let us know. We can do more of these. If it's a little rambling and you want more structure, I can do that too. But this is a new format. We think that it will be a way to get people more information in a better way. Visual learners learn visually. So if we can help you guys learn, that's what we're after, all about education. So if you have any questions about the video, if you have any topics for future videos, if you have any arguments to what I have said, get in the comments, drive that engagement. consider dropping us a like and a follow. Help us along on the YouTube journey. And if you're looking for a reloading course to take, visit us at reloadingalldday.com. Blake does a wonderful job teaching the basics of internal ballistics and what you as a hand loader need to know to get the most performance from your rifle. So, with that, we will see you guys next time.